Juan, ya se puede.
Ok, pues, bueno, bienvenidos todos. Esta es una nueva sesión de nuestro seminario de categorías de la UNAM.
Juan, ya se puede.
Ok, pues, bueno, bienvenidos todos. Esta es una nueva sesión de nuestro seminario. Ok, la ponente de hoy es Jade Master de la Universidad de California en Riverside, que nos va a hablar de redes de Petri abiertas y sus procesos. Si alguien quiere hacer alguna pregunta, por favor escríbela en el chat y podemos hacer la pregunta por ustedes. Si quieren que les quitemos el silenciador, por favor levanten la mano y pueden hacer la pregunta ustedes. También va a haber una ronda de preguntas al final de la plática y vamos a estar leyendo preguntas del canal de YouTube. So welcome everyone. This is a new session of our category seminar at UNAM. Today's speaker is Jade Master from the University of California at Riverside, who was nice enough to accept our invitation, and who will be talking about Petri nets and their open Petri nets and their processes. If you wish to ask a question, please write it in the chat and we will ask it for you. If you wish to be unmuted, please raise your hand. There will be a questions round at the end of the talk, and we will be reading questions from the live YouTube channel. So yeah, please, Jake. Thank you.
Thank you. So this is a joint work with my advisor, John Bias, who spoke at the seminar a few weeks ago. And the title, I guess, has changed a little bit, Open Petri Nets, but I'm also going to be talking a bit about the processes part that was mentioned in my abstract. So first, some motivation. Complex networks are everywhere, and they're a big problem that many mathematicians and scientists are interested in figuring out and analyzing and understanding. So here's an example of some metabolic pathways. So this is one example of a complex network that we might want to understand. Here's a circuit, another circuit that we might want to understand. And sort of the approach to trying to understand and analyze these systems that applied category has taken, and also sort of John and the students and our collaborators, is to sort of think about it in terms of syntax and semantics, which is terminology borrowed from Lavier. The idea is that you have one sort of category which represents the syntax of some type of network, and even another category which represents its semantics, which is like its actual meaning or real world effects. And then what should connect them is a functor between the syntax and the semantics. And traditionally, the syntax semantics approach has been applied to algebra, but recently applied these two papers sort of that I mentioned here by Kenny and Brendan Fong describe an approach to doing this using co-span formalisms, which I'll get into in a little bit. So sort of what's good about this approach is that in the syntax category, the composition is given by gluing. So that means that if you have a functor from the syntax category to semantics, the functoriality equation will look like this equation that I've written here. And this is great because if G and F are two networks and you glue them together, then this isomorphism relates the semantics on the larger glued together network to the semantics on each component. And this is very useful because often computing these things in semantics can be very computationally expensive or hard or difficult in some way just because the networks are so large. So it's very helpful to be able to break it up into smaller pieces. Here's a quote. I put a lot of quotes in this talk. If that's not your thing, that's okay. But I like this quote. It's sort of about how we understand things and how we make meaning by sort of having boundaries of various objects. And the boundaries are sort of what define things. So if we understand how to bind things together, then we will really understand what they are. Okay, so sort of counterintuitively, I'm not going to talk about Petri nets first. I'm going to talk about graphs. And the reason why is because my perspective on Petri nets is basically that they're a fancy sort of graph. So I think if you understand the case of graphs first, then the Petri net case will be easier. So to me, a graph is a pair of functions from a set of edges to a set of vertices, which represent source and target of each edge. Note that these are directed graphs and they can have multiple edges between a pair of nodes. And a morphism of graphs is a pair of functions between the edges and vertices, which commutes with the source and target. And that gives a category graph. So here's an example of the type of graph I mean. Here's some bus routes in Los Angeles. These are bus stations and possible maybe routes to travel between them. And what you can do with this graph is you can generate its reflexive transitive closure. And the idea is that objects of this closure will be the vertices, and the morphisms will either be identities, which represent, it's a typo, which represent doing nothing, or finite sequences of composable edges. So here's some examples of morphisms in the reflexive transitive closure of this graph I've shown. So a morphism could be traveling from Azusa to Union to Compton, or East LA to Union to Hollywood to Santa Monica, or you can just stay at Union and do nothing. Those are all examples of valid morphisms in the free category on this graph. So I've been saying free category, and it is indeed a free category. And what I mean by that is that there's a forgetful functor from cat to graph. And this process of generating the transitive reflexive closure is a left adjoint, F, which goes from the category of graphs to the category of categories. And this is a classic result in category theory. But what John and I have been thinking about is, instead of thinking about closed systems, we want to sort of open these systems up by equipping them with input and output boundaries. And the way you can do that is you stick two sets on either side, and then you have functions which map the elements of those sets into the vertices of your graph. So here's an example of an open graph. Hollywood and Santa Monica are the left inputs, and Azusa and East LA are the right inputs of this graph. If you have another open graph, so maybe this is another graph representing some routes in the larger Inland Empire. And here's another sort of left input over here and a right input over here. You can first stick them side by side. And then you can glue them together. So here, be careful what this gluing process is doing. So what it does is it takes all the nodes that are mapped to by a common element in this middle set and identifies them. So you can see that. I'll go back and forth with it. And the way you formalize this is with pushouts. So G was this graph on the left, H is this graph on the right, X, Y, and Z are these three sets with two elements, and one element. And then LX, LY, LZ are the discrete graphs on those sets. So those are graphs with that set as vertices and no edges at all. And then you stick these two cospans together, representing open graphs. And to glue them together, you take the push out over this center diagram. And that gives the gluing that I described earlier. So here's a theorem, which is, the proof is super quick, which is that the reflexive transitive closure, the left adjoint F, it preserves this gluing process of open graphs that I've been describing. And the reason is super simple and beautiful, in my opinion. It's just because F is a left adjoint, and every left adjoint preserves colimits. Therefore, it preserves pushouts, and so it preserves this gluing. But the fine print is that taking pushouts of categories is a bit more complicated than taking pushouts of graphs. So if you, so if you want to, I wish I had my writing ability. Let me see if I can draw. Nope, that's right. So that isomorphism that I showed way at the beginning of the graph for functoriality, the push out on the right-hand side, the gluing there is going to be a push out of categories that it's preserving. Oops. Sorry. Right. And when you take the push out of the free categories of these two graphs, you don't just glue all the edges together. You need to account for paths which zigzag back and forth between the two graphs. So for example, you could go from San Bernardino to Azusa to Union to Compton to East LA, and then back to Union. And that would sort of zigzag through the paths. And that is a morphism in the free category on the push out of the two graphs, which isn't contained in the free category on either of the components. So this preserving push outs process sort of has to take that into account somehow. Okay, so that's how it works for graphs. Now let's talk about Petri nets. And like I said, my attitude about Petri nets is they're fancy graphs. So a Petri net is a pair of functions from a set of transitions to the free commutative monoid on a set of species. Another way to think about the free commutative monoid on a set is you can describe it as the multi-subsets of that set, or multi-subsets with finite support. But the analogy to graphs is that T is the set of edges, and N of S, or S, is the set of vertices, and S and T are still the source and target. And like before, a morphism is going to be a function between the set of transitions and the set of places or species called S, which commute with these source and target functions. Okay, so that's what they are formally, but people start to think about them in a different sort of way usually. And the idea is that each place can be equipped with natural numbers representing the number of tokens in that place. And then the transitions can fire and draw tokens in proportion to the number of arrows going into it, and put out tokens in proportion to the number of arrows going out of it. So I have a animation that I like to share to sort of explain this, or to help visualize this. Let me share my screen again. Okay, so here's a sort of Petri net simulator, which simulates the splitting and combining of oxygen. There's three places, O, H2O, and H. O has 8 tokens in it, H has 6 tokens in it. What you can do is this transition combine is enabled, and that's why it's green, so I can click it. And I'll take 1 token from here, 1 token from here, and put 1 token here. And now that there's a token here, this transition is enabled. That's why it's green, so I can click it and it'll take in 1 token and spit out 2 tokens into H and O. And I can do this as many times as I want. And this is called the token game often. And it's sort of why people care about Petri nets, because they allow you to represent processes like these, which require and output resources. Okay. Probably some of you are already experts in Petri nets, and I apologize if this is too basic, but that's okay. All right, back to my slides. Right, so that's a token game, and there are nice mathematical ways to formalize it. And the idea is that you can freely generate a nice sort of symmetric nodal category from a Petri net, and the objects of that symmetric nodal category are going to be markings of your Petri net, i.e. elements of the free commutative monoid on your set of places. And the morphisms are going to be firing sequences. So every time I clicked, that was a firing. And a firing sequence is some sequence of those clicks. So the token game that I was talking about, that animation, is really formalized with this freely transitive closure, reflexive transitive closure process, which turns every Petri net into a free commutative nodal category. Right, and it's not just any symmetric nodal category, it's a commutative nodal category. And those are kind of weird. They're a special sort of symmetric nodal category where the monoidal product is strictly commutative. And that's sort of an awkward thing for category theorists. There's no coherence theorem relating symmetric nodal categories to strictly commutative ones. And there's also some weird sort of things that go on in terms of tensor, which I could get into, but I won't right now. But yeah, so what it is formally is a category internal to the category of commutative monoids. So this idea about freely generating commutative monoids from Petri nets was first introduced by Montanari and Masegler. And John and I sort of used a variant of their construction. And it's the idea is what I said. The objects are given by markings. The monoidal product is given by sum of markings. If you have 2 tokens and 1 token, you can add them to get 3 tokens. And morphisms are possible firing sequence. Note that the morphisms can also be added together via the monoidal product. And the adding process represents performing the firings in parallel. And there's a lot of sort of words that people use to describe this, which I think is nice and evocative to think about it in this way. You can think about it as like the solution space of a Petri net, or the reflexive transitive closure of the Petri net, or the operational semantics of a Petri net. The operational semantics basically means everything that the Petri net can do. But whatever you call it, the closure forms half of an adjunction. It's the F functor from Petri to the category of commutative monocategories. So just like with graphs, we're going to make these Petri nets open. And we're going to do in the same way. We're going to stick some finite sets on either side. Actually, they could be any sets, but finite sets are the ones you can draw. And then we're going to map the elements of those finite sets into the places of your Petri net. And in the picture that I said at the beginning with syntax and semantics, we can think about these open Petri nets as morphisms in a category of syntax. more formally, an open Petri net is a cospan in the category Petri of the following form. Here, Lx and Ly are Petri nets with no transitions and just that set as their set of places. And it turns out that a Petri net morphism from one of these discrete Petri nets to another Petri net is the same as a function from their underlying set to the places of P. So it is this picture. And you can compose Petri nets. So if you start from a Petri net from X to Y, and you take another Petri net from Y to Z, then first you can put them next to each other like this, and then identify the places which come from the same element in Y. So 4 maps to both C and E, so they get identified. And 5 maps to both D and E, so they get identified, and you end up with just one place like this. And this is formalized by using pushouts, just like before. You stick the 2 cospans representing the open Petri nets next to each other, and then take a pushout over the center to get a glued together Petri net in the middle, which works by disjoint union and modding out by the equivalence relation of pushouts. So again, like before with graphs, here's a nice theorem. The category of processes of a Petri net preserves gluing. And the proof is pretty simple, like before. F is a left adjoint, so it preserves pushouts. And the fine print is the same, just like before. Gluing of cumulative monoid categories is more complicated. So if you take the free cumulative monoid category on 2 Petri nets and then compare that to the free cumulative monoid category on the gluing of 2 Petri nets, then there's a lot of sort of new morphisms you're going to have to add, which zigzag back and forth between the 2 Petri nets in order to get them to be the same. So here's what I mean by that. So here's an example of a Petri net from X to Y and Y to Z. And here's an example of their glued together morphism. And it turns out that in this one, there's no morphism from A to D. In this one, there's no morphism from B to E. But once you glue them together, you have this path which zigzags back and forth in between the 2 Petri nets. So in the free category on the pushout, there's going to be a morphism from A to E, which isn't present in the free category on each of the components. So there's another sort of transitive closure process that you have to do in order to get everything. And if you care about the language of this gluing being nice and coherent, and you want open Petri nets to live in a symmetric monoidal category, and actually even better, they live in a symmetric monoidal double category or a bicategory. I prefer double categories. First, the monoidal category. The objects are sets. The morphisms are equivalence classes of open Petri nets. Composition of morphisms is given by pushout. And monoidal product is given by coproduct on sets and pointwise coproduct on morphisms. And what I mean by equivalence is a map between the Petri nets on the apex of each open Petri net, or an isomorphism, which commutes with both of the inputs and outputs. Right, so this is really just the shadow of a different sort of symmetric monoidal category, which I'm going to, of a double category, which I'm going to describe on my tablet. Okay, so there's a symmetric monoidal double category, open of Petri. And there's sort of different terminologies for the different components of a double category. But the zero cells or objects are sets. The horizontal morphisms are open Petri nets. The vertical morphisms are functions. And the vertical two morphisms they are going to be commuting rectangles like this. And that's the double category open in Petri. Okay. I'm going to go back to my sites and make it full screen. And similarly, you can do the same thing for open commutative monoidal categories. Make a category where the objects are sets. Oh wait, I forgot to, so let me go back to the whiteboard. Right, so that's open in Petri. You can also talk about open commutative monoidal categories, open CMCs. And an open CMC is a cospan. So we have the discrete functor from set to Petri. And then we have a functor from Petri to CMC. Which generates the free commutative monoidal category. So you can compose them, and an open CMC is going to be a cospan of this form. So these are discrete categories on the set X. They have no non-identity morphisms. So a map from that to C is just going to pick out some of the objects of the commutative monoidal category in the middle. And like Petri nets, you can compose them using push out. CMC has all push outs. And that algebra of composition also forms a double category called open of CMC. Where the objects are sets like before. The morphisms are the horizontal morphisms are cospans like this. Horizontal composition is by pushout. Vertical morphisms are functions. And two morphisms are the similar sort of diagram that I drew before. Which commutes. So these are FL of some function F, FL of some function G. This is some commutative monoidal functor, which is a functor between the categories, which preserves the monoidal product. And these squares commute. And the last fact is that this process of applying open is functorial. And what I mean by that is that we can take the diagram Petri set this diagram of functors. F circ L, L, and F. And this diagram induces a symmetric monoidal double functor. Which is a pretty complicated object. I grant you that. But what it does, we call it open of F. From open Petri to open CMC. Okay, back to the slides. Right, so you get this monoidal double functor. It's actually a symmetric monoidal double functor. And what it does is it's given by pointwise application of F. So for an open Petri net, which is a cosband, it applies the free commutative modal category on each piece. And it turns it into its open category processes. And like I said before, because F is a left adjoint, it preserves pushouts. And that's sort of where the functoriality of this double functor comes from, the preservation of these pushouts. And really what this is saying is that, open Petri nets and open CMCs, they both form coherent languages because they're described by these double categories. And the functor is now a coherent mapping between those languages. That's sort of informal. I don't have a precise statement to back that up. But that's sort of the motivation and intuition behind it. So let me check the time. Okay, so now I'm going to switch gears a little bit and talk about a different sort of functor out of open Petri nets called the reachability semantics. So the reachability problem, it asks for a Petri net and two markings of the Petri net, which is an assignment of tokens to each place. Is there a sequence of firings which takes the first marking to the second? And the reason why people care about reachability is if your Petri net is representing some process or program that you care about, reachability is the same as asking, does your program run, or does your process reach the intended goal? So the reachability problem is decidable, so that's good. But its complexity is gigantic. Its time complexity is greater than any primitive recursive function. So that's really big. It's bigger than exponential, bigger than anything really. Anything you could, any primitive recursive function that you would reasonably write down. And the analog of reachability for Turing machines is the halting problem. So the halting problem is a little bit different for Turing machines. And it's almost, it's decidable, but just barely. So this puts them in a sort of sweet spot of expressiveness. That makes them very interesting. Okay, so open Petri nets are a nice setting, in my opinion, to discuss reachability. If you have an open Petri net, you can define its reachability relation just on the inputs and outputs rather than all of the places, as the subset of the free commutative monoids on the inputs and outputs, i.e. the markings which are reachable, contains an element xy if y is reachable from x. So here's an example of the reachability relation. If you take this open Petri net, you can equip it with a marking, and that's what these two black dots here are. So first you push those markings onto the two places. And then you can fire this blue transition, which takes in the 2 and outputs 2, it puts them there. And then you can fire this blue transition on top twice. And then you can push them into the output. So that means that this marking on the input that we started with here, or this output, is reachable from the one we started from the input. And all of this can be made categorical. Really, this idea about reachability is really talking about connectivity of your category. So if you have a Petri net, then a marking n is reachable from n if and only if there's a morphism from m to n in the free commutative monoid category. So really, we can think about this for any sort of cospan of categories and take its connectivity as a relation on the objects of x and y, which says that, which contains an element if and only if there's a morphism from I of x to j of y. So to get the reachability relation of an open Petri net, first you can apply the semantics functor, and then you can take the connectivity of this, or the reachability of this. And this process is functorial from the double category of open Petri nets. What is it functorial into? Well, it's functorial into the double category rel, where objects are sets, morphisms are relations, vertical morphisms are functions, and a 2-cell between relations is a square, satisfying with an inclusion filling the center of it. So if x and y is in the first relation, then f of x, g of y is in the second relation. And this reachability process is also a symmetric monoidal double functor. And it makes this assignment on morphisms. It turns an open Petri net into its reachability relation. If you wanted to sort of prove this, the way to do it is to construct it as the composite of the first functor, which we talked about earlier, from Petri nets to their free reflexive transitive closures, And then you compose that with the connectivity functor to the category of relations. Okay, but there's also fine print on this one. It is a double functor, but sort of the default, depends on who you ask, but the default notion for double functor is lax. So it's not that the composite of P and Q, there's not an equality here, only an inclusion. So it's not, it doesn't, you definitely, the sum of two systems is greater than the sum of its parts. But they're still sort of bounded by below by the sum of its parts, which is a very useful fact if you're trying to model things. And people who are sort of interested in this fact are, there's some companies, there's a company called Statebox, which is working on making a programming language using Petri nets and open Petri nets. There's a piece of software called Penrose, which is a reachability checker for Petri nets. And the way it works is it breaks the Petri nets into smaller components, checks the reachability on each piece, and then glues those reachabilities together. And sort of part of my thesis work, something I'm interested in is generalizing these ideas to other contexts, which I won't get into much. And now I'm pretty much finished, which is good. I'm going to end with a quote from Growth and Deek, who talked about, maybe you've heard this quote, but I really like it. The idea is that there's two ways to solve a math problem, and either you can attack it head on and crack it like you would a walnut, or you can put the walnut in water and let it soak until you can break it open easily with your hands. And the approach that I think category theory often takes in applied category theory is the second approach of letting things soak for a bit. And that's sort of what this work also aims to do. We're not trying to solve the reachability problem directly. We're just sort of trying to build a lot of structure around it until we get nice insights which just start popping out. And here's the references. And that's all I have to say.
Well, thank you very much, Jade, for a beautiful presentation. It's very nice. Thank you.
Thank you for having me.
Yeah, thank you for accepting the invitation. Does anyone have any questions or comments?
Hi, I have a question. This result you mentioned about the reachability problem being decidable, but just barely, that the complexity grows faster than the primitive recursive function. I don't think I've seen another problem in that situation. That sounds pretty crazy. Did you have any, maybe just the idea of the proof is too complicated, but do you have anything you can tell me about how you prove that the complexity grows that fast?
Well, I guess some sort of intuition about it is the thing I was talking about. Yes, so I'm not an expert in those topics, so I don't really know the proof at all, really. But I at least some intuition about it is how quickly or how difficult it is to sort of glue together reachability,
right?
Because you really have to account for everything which goes between. So that must be related to how complex it is somehow.
That's what the third paper in your references is about? That's the paper?
Yes. Mm-hmm.
Okay, thank you.
You're welcome.
I just have one small comment here. As a category theorist, strict symmetric monoidal categories seem like a really terrible concept, but since it's a category internal to commutative monoids, and a monoid is a category, so this is a double category. It's a nice strict double category, so I like it.
Yeah, that's really interesting. I didn't really think of it that way. It's a degenerate sort of double category because in one direction there's only one object.
Yes.
But still, it's really interesting. Yeah, the commutative modal categories are also nice because they're algebras of a Liouville theory, so they're complete and co-complete.
Yes.
Yeah, they've got lots of nice properties, but there are some issues which I could show you if you would like.
Okay. Yes.
Okay, let me show you something. So actually most PetriNet people prefer not to use commutative modal categories because they do kind of weird things with the processes. So for example, you can take a bunch of morphisms like this. So here's a string diagram. So this is 1 on y, and maybe this is x. And yeah, maybe this is also x and also x. Or maybe this is 1 sub x, sorry. So first you can split this up in half. And then because it's commutative, you can turn the second one like this. Yeah, 1 sub x. And then you can glue it together again. And slide them past each other. And so this is kind of weird because it's saying, if you think about this in terms of processes, it's saying that 2 processes performed in parallel are the same as 2 processes performed in sequence.
Yes.
So the solution to this is to use like other sorts of symmetric modal categories which aren't strictly commutative. And there's a lot of work about generating those, but it's harder because PetriNets are based in free commutative monoids.
Yes.
Yeah, so if you want to make something that's not commutative, it takes some work, but it can be done.
Interesting.
Well, what kind of work do you have to do to get non-trivial symmetry? Or, I mean, just a general.
Right, so there's a paper, or I guess I'll just tell you. Well, that's great. Okay, so I'll tell you the approach that I like, which is instead of starting with PetriNets, you start with these things called pre-nets. And a prenet is like a Petri net, except instead of a free commutative monoid, you have a free regular monoid. And the pictures of them now have an ordering on the inputs and outputs. So it's like this one goes in first, this one goes in second. This one goes out first, there's only one of them. And prenets freely generate strict symmetric monodal categories. So there's an adjunction like this, which is nice. But still, this isn't good enough for some people because prenets aren't Petri nets. The people who use them want to be able to just write down a Petri net without an order and not worrying about making an arbitrary ordering on the inputs and outputs. So this is a work in progress, but there's sort of like a middle ground between Petri nets and prenets. Called sigma nets, which this isn't out. This is something I'm currently writing with some other people. And what do these go into? All right. So actually, it turns out that first prenets go into just monoidal categories, and then sigma nets sort of generate symmetric monodal categories or strict symmetric monodal categories right off the bat. And then you have these sort of commutative diagrams between them. Sigma nets are kind of complicated. The idea is that instead of having a set of species, you have a groupoid of species, which are equipped with sort of these permutation and action of the symmetric group. Yeah, so like instead of having an ordering, you have their prenets equipped with an action of the symmetric group on these. So it's saying, oh, you have this ordering, but also you're allowed to switch them. And that's sort of included in your generating data, which allows you to generate symmetric monodal categories without having to choose, really. That's probably more than you asked for. Did that answer your question?
So is this, oh, sorry, is this related to so Joe talked about network models. Yeah, last week. Are sigma nets related to network models in some way?
Let me try to remember the definition of a sigma net. Right, so I don't think they're really related. They might be actually. I haven't really thought about it. What's a network model? It's a functor from the symmetric groupoid to set. Is that right?
Well, I thought it was.
I think so.
Yeah.
Okay. Yeah, and a sigma net is a functor like this. So, or maybe write x instead of s. So P of x is the free symmetric monodal category in x. So it's, you take the set x and then you right, so you equip it with all the symmetries. I'm pretty sure. Yeah. Yeah, so it's the objects are lists in X, and the morphisms are all possible symmetries. And the idea behind sigma nets is that if you have a list like A, B, A, and C, this will map to the set of transitions with source A, B, A, and target. see. And yeah, I don't know if this was related to network models, but that's a nice observation because they do, at least superficially, seem kind of similar.
Okay, yeah, thank you. Well, so I do have another question, I'm sorry.
Yeah, absolutely.
So is there an open Petri net counterpart of, so you already mentioned that commutative monoidal categories are rather strange and probably undesirable. But so how about strictly involutive commutative monoidal categories?
How about what sort of commutative monoidal categories? Sorry, I missed that.
Sorry, strictly involutive. So yeah, they have an involution, strict involution. So
I don't know what that is.
Oh, sorry. Well, yeah, I can look for that. So, but so you mentioned there's so Petri nets are sort of fancy graphs, is there a way of making them fancier? Well, you already mentioned sigma nets and so on, but does making your Petri nets, open Petri nets fancier translate always to something fancier on the commutative monoidal category counterpart?
Yeah, so this is sort of the key diagram that I think is relevant. So there's prenets and so if you add these sort of actions of the symmetric group on your transitions, add that to prenets, then you can generate these symmetric monoidal categories. But I guess you were talking about involutions.
Yep.
So an involution is a functor from the category to itself, which squares to the identity.
Right. Yeah.
Okay. Yeah, I have no idea, to be honest, what that would do.
Okay.
Maybe it's true there is sort of a duality between places and transitions. You can sort of turn them around and turn one into the other. So maybe that's an involution.
Okay.
It's just a guess, but yeah, I'm not sure.
Okay.
It's an interesting question, though.
Does anyone else have any questions or comments? Is there a way to, so open Petri nets in different directions, not just in the domain and codomain direction? So suppose, well, I don't know. It's just a very vague question, I'm sorry. But.
Oh, well, yeah, open of Petri is I think a dagger category. So cospans can be regarded in either way. So like, you can think of this as P from X to Y, or you could just write it the other direction, or P from Y to X. And I'm pretty sure that gives a dagger on open of Petri. And I think a reference for this would be, well, not exactly this fact, but in Brendan Fong's thesis, he talks about these sort of structured cospan categories or decorated cospan categories, and he proves that they're hypergraph categories. And I think he also proves that they have these involution, these nice dagger properties.
Okay.
His thesis is what I would recommend for more about that. But yeah, this is a dagger.
Okay. Okay, thank you.
You're welcome.
Well, yeah, I have another question. I'm sorry.
No,
so
absolutely. They're great.
So with a reachability double functor, the reachability relation double functor, so you mentioned that's lax. Is there a way to making your double domain double category smaller in order to get a strong, I don't know, monoidal double functor.
Right. So, like, is there some subcategory where it's not lax? Is what you're asking?
Yeah.
And I think that's true. Yeah. So if your nets only flow in one direction, then they'll compose exactly. And I think those are called workflow nets.
Okay.
So those are nets which, yeah, like you can have branchings, but really they only go one way. They never, oops, there should be places. Pretend there's places. Yeah, and if you compose these, you're not going to get any zigzags going back and forth. So that issue I mentioned is not going to happen.
Okay. Okay, so in that case, you'll get the equality between the composition of the reachability relations. Okay.
Thing is, as it is now, none of these facts are probably things which would be surprising to most people who study Petri nets. At least to me, the interesting part is the way they're organized into this larger picture as a double functor. But this, if you told a person who like works on Petri nets and it was more practical or applied, they would probably say like, oh yeah, obviously you can compose reachability of workflow nets. Like obviously it's bounded from below. So these aren't like new facts which are being proven. They're more like interesting ways to frame old facts and understand them.
Well, yeah. Well, so I'm not sure if it's in that direction, but is the double category of open Petri nets fibrant or something like that?
Yes, it is actually. Yes.
Okay.
I can't believe I knew that. But yeah, so it turns out that every structured cospan category that you make is fibrant and therefore turns into a symmetric monoidal bicategory when you take the horizontal bicategory of it.
Okay.
And that's proved by Kenny Corser.
Yeah.
And you can find it in his thesis, I think.
Okay. Yeah, thank you.
Yeah, you're welcome.
Yeah, I think that's it for me.
Okay.
Does anyone else have any questions or comments? Well, if not, yeah, let's thank Jade again. Thank you very much, Jade.
Yeah, thank you.
Yeah, it's a
See
very
you some
nice
other
series.
time.
Yeah, it's a very nice series of talks on Petri nets, I think. Yeah, we're very happy about it. Thank you so much.
Yep, you're welcome. What's your interest in Petri nets, if you don't mind me asking?
Well, so we're studying models for quantum field theory. So it's local models. And well, on the one hand, double categories appear almost everywhere. You have this, yeah,